So looking at the second video of the series of videos on the scanning vibrometer measurements of this cantilever beam, here I'm just going to have a look at the software options in here. So I talked about the 2D alignment previously, and we do that by identifying a series of points on the structure and somewhere off the structure but in the plane of the structure. And this is the 2D alignment process. We can also do 3-dimensional alignment, which will take into account some depth, but our structure in this case is simply a 2-dimensional structure. The 2D alignment has been completed, and so we have alignment of the camera system and the vibrometer scanning system. So we can then define these measurement points, and you can just about see in the video I showed in the previous video that the laser beam moves on the structure as we click from point to point. As we'll move it to the top, I'm just clicking different points in here. In terms of the A to D set at the acquisition settings, we're currently acquiring a fast Fourier transform mode. We're doing 5 complex averages per point. We can specify the vibrometer sensitivity, which is actually controlled from down here, 250 millimeters per second sensitivity, so we get calibrated units. We have the force transducer, which I showed, mounted to the shaker via the stinger with a range of 1 volt and a sensitivity of 10 millivolts per Newton. We have the option to turn on some filters, but we haven't specified them. We can also define the frequency range, which should be the range of interest or associated with the resonances of the structure that we're interested in capturing. We can define the sample time, which is the reciprocal of the resolution. So the number of lines in the spectrum, this is standard digital signal processing or acquisition parameters. The finer the resolution of the spectrum, the longer we collect data for. You can hear currently that the chirp is quite a slow chirp, over somewhat less than 6.4 seconds. We'll have a look at how that's generated later. We have the option to set some windowing in the normal way. We can, with a burst chirp, we can use a rectangular window. And when we collect our averages, we use an internal triggering option because we're generating this pulse within the instrument, and therefore we can set our triggering up from within the instrument from an internal trigger. If we were using an external function generator, we might choose to do triggering on the reference channel, which is from our force transducer. We have an option to do some speckle tracking for when we have some relative motion between the target and the instrument, but in this case everything's relatively stable. Here you can see we can apply a tracking filter and a velocity sensitivity. There are a number of options for those, and we should set the sensitivity of the instrument according to the amount of vibration that we expect at the largest amplitude case, so at the tip of the cantilever beam in this case. Here are the options for the generator that's driving the shaker, the function that's being played with through the shaker, and we're currently choosing a burst chirp. Other measurements of interest that we've collected some data for would be a burst random, and the burst start and length is defined here, so we can start 5% of the way through the per averaged time block and end after 30%, and that allows the resonance to slowly decay before the start of the next time block, and therefore we minimize problems that might occur as a result of leakage. So if I click burst random and hit the OK button, now you can hear a different type of measurement, a different type of excitation, a burst random signal. Okay, in the measurement window, if I tile these and we have a look at the the time domain referencing, this is the force transducer. You can see that that's a burst random signal here. So this is the burst, this is 5%, it ends after 30%, and then the energy decays. Here you can see the FRF that's being collected, response in millimeters divided by the excitation force. So there are a number of different types of measurement of excitation signal as mentioned in the last video.